similarly, these allenes are also differently substituted, both the terminal centers. And this is a three-dimensional structure of the allene I have shown. You can also have a six-membered ring where you have a 1,3 substituents. One is like axial methyl, one is equatorial methyl. So there is no plane of symmetry you can draw in this molecule. So this will be chiral. Next one we learned was the center of symmetry. That if you have a cyclobutane and two methyl groups, and then there is a center. From center, if you go to the like opposite directions, you can hit the same atom, and then identical atoms, and then you say that okay, it has a center of symmetry. So you have a tartaric acid kind of structure where carboxyl group above here, and then you go through that plane and go to the other side, extend by the same length, and then you get another substituent. So it has a center of symmetry. Third one we talked about is like a little confusing sometimes, but if you practice it, you will get to know that we have drawn a Sohart structure as shown here. Carboxylic group up here, carboxylic group down here, and pass an axis through this molecule, this CC bond, and then rotate it by, we have rotated by 180 degrees. Sometimes it depends on what angle you rotate it, and it can be like a 90 degree, and then it will be called S4 axis of symmetry. And then like after rotating, you can see the carboxyl group has come down and the backside carboxyl has gone up, and then against this axis you put a mirror and construct its mirror image as shown here at the bottom. And then you can see, of course, the color is red, but then you can see that these two molecules are identical. So then you can say this has a S2 or twofold axis of alternating symmetry. And last one we talked about is a simpler proper axis of symmetry. Here you can see that methyl group is here, this one is there, and then you can have a C2 axis going through this molecule, because if you rotate, remember that after rotating you don't do any more exercise. That you don't put a mirror, you don't put like invert the molecule, and so it should be clear to you that it will completely identical, because as you can see that C2 axis is here. If you rotate, you basically get the same molecule, so you don't have to break your head to find out if this molecule is identical to the original molecule or not. Benzene ring can have many C2 axis of symmetry. It could be through this, like a hydrogen, carbon, and this one, and then carbon, and then this hydrogen, or it can have through this bond. Those are all C2 symmetric, or you can have it also in the middle, and so you can rotate it by 60 degree, and then you can see that you are getting an identical molecule. So since it is 360 by 60, so you call it C6 axis of symmetry. So if you have a molecule where any of those like elements of symmetry are present, then you call it like it is not optically active, it is a achiral molecule. And if all of them are absent, then we call chiral disymmetric, and on top of it simple axis of symmetry, then you call it chiral asymmetric. But so just like a simple axis of symmetry, if it is present, does not mean that molecule will be achiral. So this other three, of course, they are like elements of symmetry, which the presence of them make the molecule not achiral, not chiral. And then after knowing how to find out the molecule is chiral or not, that is elements of symmetry, we talked about how do like give them configurational nomenclature to those chiral centers. For that we learned how to draw a Fisher projections. So Fisher projection, you draw two lines. One is horizontal line, and then like bisect it with a vertical line. And the horizontal line is always for the atoms coming, substituents will be towards you above the plane. So chlorine and bromine, for example, like you can see from the ball and stick structure, towards you, and the other two substituents and hydrogen are below the plane. And so I have showed you like this structure, for example, on the left hand side on the top structure, you have to draw like this: carboxylic group towards you, hydrogen towards you, hydroxyl is going below the plane. So dashed lines represent like a substituents going below the plane, and this one, dark lines, bold lines coming, bonds coming towards you. So you can't, rotate the molecule by 90 degree, because then it will show a different chirality. So we'll come to that, how to give this nomenclature R and L. Yeah. And but what is allowed, you can have in the bottom, you have shown the structure here. So hydroxyl, suppose you catch hold of that hydroxyl, don't allow it to rotate, but rotate the other three. So if you rotate by clockwise manner, then carboxyl group will come here, CH2 will go there, and hydrogen will go there. Hydroxyl will remain in the same place. So then you are not changing the chirality of the molecule, and you can possibly you don't have the three-dimensional structure. Otherwise, you could have done it, by physically holding that bond and rotating the front side, like three other atoms, and either clockwise or anti-clockwise. So it will not, change the chirality of the molecule. So if you are given a Fischer projection structure, make sure that you are not allowed to rotate it by 90 degree. And so configuration we learned, D and L. So it originated from the glyceraldehyde structure. So you put the one which has a higher priority on your
Sir, you're muted.
yes. Okay. Can you see the slide?
Yes, sir.
Okay, sorry. Pointer, the pointer. Okay. So you have oxidized on the top, reduced form on the bottom, and if you write like this, and hydroxyl come, and then in case of glyceraldehyde, people found that this is a positive, like a dextrorotatory, and rotates. We'll come to that one, optical activity and all. And then the term gave the configurational nomenclature this compound as a D plus. And so from there we went to give the configuration nomenclature to amino acids. For example, it does not have the hydroxyl, but it has an amine, and this amine you have to write on the right hand side, and then you can see just like glyceraldehyde, and oxidized from the top, that is carboxylate, and side chain at the bottom. And we still use this nomenclature, as I said, D amino acid and L amino acid, so on. So all the natural amino acids that we have in our body and most of the biological system are L amino acid. And similarly, all the sugars, we call it, right-handed sugar, because basically the rotation is positive, and that is why they call right-handed sugar, D-glucose, and then mannose and galactose and so on. You can have, and you can see that L minus glucose is complete mirror image of the D plus glucose. So all the chiral centers are different. Just because I have written differently, you can see that the stereochemistries will come different. And so the but we are already, to give the nomenclature like a D or L, you have to look only for the C6 carbon and C5 carbon. And then you can see the hydroxyl on the left hand side. So it is a L minus glucose, and D plus mannose and D plus galactose and so on. These are all, hexose sugar. Now, but more, like a recent or, like a later nomenclature, which most of us we use all the time, is called R and S nomenclature. So this was proposed by Kahn, Ingold, and Prelog, and in 1966. And those who are interested can read this beautiful, article which appeared in Angewandte Chemie 1 journal in 2016. That was the 50th anniversary of this CIP nomenclature. And so in this one, what you do is like a carbon has 4 substituents, so you give priorities, to those substituents. First priority, which has the highest priority, then second highest priority, and third one, and the fourth one. The one which has the lowest priority is I have designated as 4. And then, like you look at the molecule in such a way that lowest priority one stays away from you. So your eyes are here, you're looking at this carbon atom, and 4 is away from you. And then if you have to see how you go from 1 to 2 to 3. If you go anti-clockwise manner, then we call it R. And if from 1 to 2 to 3, if you go anti-clockwise fashion, which is like a mirror image of this R, is called S. So it's simple. So the only thing you have to remember that lowest priority goes away from you. And how do you give the priorities? There are a few rules are there that very simple. So you must have learned all these things. Atomic number higher one, which will precede, for example, sulfur more than fluorine, more than oxygen, more than nitrogen, than carbon and hydrogen. Similarly, if you have the atomic mass number, like isotopes for tritium and then deuterium and then hydrogen, so this one tritium will get a priority. Then when two atoms are identical, then you can see what are the atoms attached to them, right? So you have a situation where you have an ethyl group and one methyl group, CH3. And then you have to first go from first one to second one to third one. So if first one cannot decide, then you go to the second atom. Second atom cannot decide, go to the third. In this case, the first one, that is green colored, I have put here. What are the different substituents? So you can write in this kind of bracket, and then you can see that that you have written that this carbon green color is attached to one carbon, one hydrogen, and one hydrogen, two hydrogen. And I have put the one which has a higher atomic number first, and then go to the second one, which and third one, of course, in this case are same. And if you compare it with a methyl, then you put again the substituents in the bracket. You can see hydrogen, hydrogen, hydrogen. And so this one has a higher priority, and carbon, and so you give that ethyl group as a higher priority than a methyl group. So it outranks the methyl group in terms of priority. So you can do the similar exercise here. For example, instead of ethyl, I have written CH2OH. So you can write carbon here, and then within the bracket you will write one oxygen. Oxygen you will write first, and then you can write a hydrogen, hydrogen. And this will be more than the second one, which is a CH2 amine, because then in the bracket you will write nitrogen, then comma hydrogen, then comma hydrogen. And since like a oxygen has a higher priority than nitrogen, so CH2OH as a whole will have a more priority than CH2NH2. And suppose like you have the same groups attached here. For example, third one I am shown here. Within the bracket, if you write, it will be C, comma H, comma H. And this one also, on the fourth one also, C, comma H, comma H. So the first atom you are not able to decide. Then you go to the next one. And in the next one, you can see that you have a bromine. So you write bromine, and then fluorine and hydrogen. In this case, chlorine, fluorine, and hydrogen. And then you can say which one gets a higher priority. So CH2, CHFBr gets higher priority than the next one. So do this little bit exercise. There is a different substituents, and then it will come naturally to you. You don't have to do this even exercise. And just looking at the substituent itself, you should be able to say that which substituent has a higher priority. Now, fourth rule is like a work outward from the point of attachment. As I say, like you go from the first atom, and if you are able to decide in the first atom itself, you don't go to the second atom. For example, you have an isopropyl group, CH, CH3, CH3, and you have a CH2, CH2, OH. So the first one you can put in what are the substituent attached to the first atom, that is green color atom. You have a two carbon, C, C, and H. Second one, you have C, H, H. So in the first atom itself, we are able to decide that this one has a higher priority than the second one. You don't have to go oxygen. Sometimes you may get confused because I have an isopropyl group and I have a CH2CH2OH. Oxygen has higher priority, and why should this one not get a higher priority? It is because that we have been able to decide in the first atom itself that this has a higher priority. Then we don't go to the next atom, that is next carbon atom, that is which is bearing the oxygen. And so the first atom you have this one a higher priority. So this is the fourth rule. And evaluate the substituents like a one by one. And like if you have simple thing, don't add the atomic numbers within the group. So you have a CH2OH, and then you have a tertiary butyl group, carbon attached to 3-methyl group. Now, if you write the substituent, as I've said before, you write oxygen and then hydrogen and hydrogen. And this one has a carbon C, C, and C. So within that ring also, you don't add those, like a 3 atomic numbers we are not adding. So the first atom itself, which has a higher priority, we have put in the beginning in the first, and then this has a higher priority than the second one because this has a carbon. And then we don't go. If you are able to decide at that stage itself, we don't go to hydrogen and hydrogen or carbon and carbon and the other 2 atoms. So CH2OH outranks tertiary butyl group. So this is the 5th rule. I'll go back to this. First, as I said, like higher atomic number precedes the lower. So if you have a higher atomic number, it will have a higher priority. Higher mass number within the same element. So if the isotopes are there, so the higher atomic mass number isotope will get a priority mode. And then if you have 2 or more atoms, if the first atom itself you are able to decide, then you don't go to the second one and you write like this. This is the again another similar very rule. The first one itself we are able to decide which one has a higher priority. And then again, like within a substituent, then you have oxygen, hydrogen, hydrogen. This one has a CCC, but this one gets on the left hand side a priority. And then the 6th rule comes, which are like multiple bonds between the 2 atoms. When you have a substituents, like for example here you have an aldehyde, and this aldehyde will outrank an alcohol CH2OH because when you have a double bond, we put 2 oxygen as if like this carbon is attached to 2 oxygen. So then I write within the bracket 1 oxygen, 2nd oxygen, and 1 hydrogen. Whereas when I have a CH2OH, I have written OH and H. So this one has a the duplicate atoms in parentheses except for hydrogen are made up of ligands of 4 of the what we call phantom atoms of the atomic number 0. So anyway, don't go through all this terminology. Basically, you just multiply this as many bonds you have, and you put the same atom here, and then that's why aldehyde gets higher priority than an alcohol. I have written here some examples on the right hand side in the white colored portion, that you get a carboxylic group, CO2H, and then the way you have to write, this carbon is attached to hydroxyl, this carbon is also attached to 1 oxygen, right? This is oxygen. And since I have said that it has a multiple bonds, so I have also attached this carbon with another oxygen. We have kept with parentheses because it shows that it's kind of phantom atom and this. And then this oxygen, which was double bonded to carbon. So I have 1 bond is already there, right? C oxygen to carbon. But this oxygen, since it is double bonded, I have put another carbon here, right? So you compare this one with a COH3. So if you have hydroxyl, hydroxyl, and hydroxyl, now you can see that this carbon is 1 hydroxyl identical, but this oxygen is attached to a hydrogen, whereas this oxygen is attached to a carbon. And similarly, oxygen is attached to a hydrogen, and so This oxygen is a phantom oxygen, more atomic number. So based on this one, so we can say this has a higher priority than COH3 because whereas this oxygen is attached to a hydrogen, this oxygen is attached to a carbon. And similarly, if you have a double bond olefin, so you can write the same way that carbon is attached to one hydrogen and then two bonds are there. So one carbon is here and one is like right with the same carbon you put here. Similarly, the terminal CH2, so I have written a CH2, two hydrogens are there, but this also attached to two carbon as if. So this has a higher priority than an isopropyl group, because isopropyl group you can see has a one carbon attached to a methyl group that is similar to this one carbon attached to another methyl carbon here, one is hydrogen, but in one of the carbon here is attached to a carbon. So this is not a, this is a CH3 here, this is a CH2C kind of thing. So that is why the rule is that this gets a priority. This double bonded olefin has a higher priority than isopropyl group. And same exercise now we do for the C triple bond CH. And as like a now it was attached to two carbon and now it is attached to three carbon. So one is like a C, this C here, and then C to another C here, another C here, and the terminal one attached to one hydrogen, and as if like it is attached to this previous carbon, so two carbons you put, and this gets higher priority than tertiary butyl group, because tertiary butyl group has 3 CH3, whereas this carbon has one carbon here, one carbon, and this second carbon is attached to two carbons. So that's why I am giving higher priority to acetylene. And last example is nitrile group, C triple bond nitrogen. So same as in acetylene, carbon attached to one nitrogen, carbon attached to another nitrogen, carbon attached to one nitrogen, and this nitrogen is attached to one carbon, and this nitrogen attached to another carbon, and this nitrogen here. And you can see that I have written another structure here where this nitrogen attached to two carbon, this NN dimethyl, two substituents are there, and this carbon. So this one has a higher priority than this one, because that nitrogen you have hydrogen here, whereas this one has a 3 nitrogen. So obviously this is a higher priority, and which has more priority than the last one because it has only 1 nitrogen. So these are the small exercise you have to do where these atoms are attached with through another atom by multiple bonds, like aldehyde, carboxylic acid, then olefin and acetylene, and so on. So these are the CIP rules, and as per CIP rule, suppose if you go, for example, lactic acid, and as I said, like lactic acid has 2 isomers possible because there is only one chiral center, and the priority of hydroxyl, very obvious to you, it has a higher atomic number, is 1. And the second one will be this one. So you don't have to do all this exercise that I have done before. So by looking at the substituent itself, you are able to say which one has the second priority. So this has the second priority, and methyl has the third priority, and hydrogen is the fourth priority. So I have drawn the structure in such a way that hydrogen is away from me. So, and you are looking from this side of the molecule. And in order to go from 1 to 2 to 3, so you are going anti-clockwise. So we call it S. And its mirror image, of course, like when you go from 1 to 2 to 3, so you go clockwise fashion, R. So this is the two, stereochemistry that you can get from lactic acid. And this can also be extended, to olefins. And very similar rules to say that if olefin is cis or trans. So if it is cis, we call it Susamen or Z sometime. And if it is trans, it is called Engegen, E, or it is called trans. And here once again, like you have the substituents on the two carbons. Of course, you have a double bond here in the middle. And these two, substituents of one of the carbon, so you find out which one has a higher priority. So this carbon has a two substituent. One is written in this kind of bluish, and then you have a white one. So say this one is a higher priority, this one is a lower. And on the other carbon, then you go, it has a lower priority, and the red one has a higher priority. And so higher priority of one carbon and higher priority, if they are on the opposite side, and then you call them trans. And if those two, like substituents of the higher priority are on the same side, we call them cis. And to determine the priorities of these substituents, you follow the same CIP rules. For this is now application extension of the CIP rule for determining the geometric isomers, cis or trans of the olefin. For example, now you have these substituents here, the methyl and butene, right? 2-butene. So I call it a cis-2-butene because this carbon has a methyl, it has a higher priority, and the hydrogen has a lower priority. This has a methyl higher priority, this has a lower priority. So two methyls of the higher priority on the same side. So I call it cis. Lower substituents have different other, substrate has different other substituents. You have a bromine, you have a chlorine. Out of these two, bromine has a higher priority than chlorine. And at the bottom one, you have an ethyl group and one methyl group. So ethyl group has a higher priority than the methyl one. So if you overall you look at the structure, then you can see that in both the carbon, the higher priority group are on the same side. So this is a cis structure. And if I, of course, exchange these substituents, interchange, the bromine comes to the left-hand side and chlorine here, then you can see the one which has a higher priority like a bromine and this ethyl group are opposite. So it is called it trans or N-Gegen or E. And the top one also, this is trans 2-butene or E2-butene, sometimes we write. So very similar to determine the geometric isomer cis or trans. Again, very similar, higher atomic number outranks lower atomic number. So in this substrate, you have a bromine, you have a fluorine. So bromine has a higher priority than fluorine, and this one, chlorine, has a higher priority, this one. So two higher ones on the same side. So this is a cis olefin. Sometimes people also try to assign, you can say that configuration by drawing from the Fischer projection. But you don't do that exercise, but it's good to know. For example, I have drawn S lactic acid on the left-hand side. And this structure, as you can see, I can draw like this, right? On the middle, where carboxyl group is above the plane, methyl is down. Basically, I've little bit rotated the this left-hand side structure, rotated by say 90. And if you rotate 90 degrees, you can see the carboxyl group is above the plane. This hydrogen also comes. This hydrogen which are below the plane now coming above you, above the plane. And this hydroxyl is below, and this methyl is below. And then if you draw a Fischer projection, it will look like this, because I have said that Fischer projection, hydrogen and carboxyl and methyl, and these two are horizontal line. They are above the plane, and vertical lines are below the plane. Now here you go like a higher priority is the OH, and then the carboxyl group and the methyl group. And then I'm going anti-clockwise when your lowest priority on the left-hand side. And then since we call it S. Normally, like in three-dimensional form, if I have written here, if you go anti-clockwise, then it becomes S. The lowest priority on your left-hand side, and you go like this, then you call it S. So clockwise is S. But don't get confused by this Fischer projection. It is better to draw the structure on the left-hand side as it is drawn. And whatever you do, like you have to get a three-dimensionality feeling for this molecule when you assign the stereochemistry. And you have now molecules where you have a more than one chiral center. And this is again like a Fischer projection. And in order to determine the stereochemistry of this molecule, you have to go back and draw the Fischer projection as shown here. Then it will become clear to you from the Fischer projection your three-dimensional structure, and then you can see that this hydrogen is coming above the plane, this one is coming above the plane, this bond is below the plane, and this bond is below the plane. And then you can do this exercise. This is a stereochemistry is R. This go anti-clockwise. Suppose you do by Fischer projection lowest priority here, and then this is the highest priority. This one is the second priority, and this one is the third priority. So you go anti-clockwise, but you call it R. And then the same thing here. There's a hydroxyl and this carboxylic group, and this one is the third priority. So you are going anti-clockwise. These also are, and its mirror image is shown here. This R becomes now S. You do the same exercise. So you have OH here, higher priority. This is second one. These are going clockwise. This is S, because I am saying that these are from the Fischer projection. But you can draw the three-dimensional structure as I have shown before, 2 bonds above the plane, 1 bond below the plane, and like that. This has a higher priority, oxygen. This is going to carbon, and this is the third one. So fourth priority, you don't worry about. You go like this. It is clockwise, so this is S. And you can have also a situation where like because as I said, like if you have a n number of chiral centers, so number of possible isomers are 2 to the power n. Tartaric acid has 2 chiral centers, so it is 2 to the power 2. That means it has a 4 possible isomer. So this 3 of them are shown here, but 4 of them are shown here. These 2 are identical, and they are called meso. And you can see that these 2 I have called enantiomers. This is a complete mirror image of this one. So all chiral centers of one molecule is different from the chiral centers of its mirror image. So enantiomers of a chiral molecule are those stereoisomers that are mirror images of each other and that are non-superimposed. Enantiomers have different configuration of all the stereocenter present in the molecule. And whereas these 2 are diastereomers. I mean, same thing is like this one, first one and the third one are diastereomers, where if you have 2 or more stereocenters, and at least 1 or more equivalent stereocenters will not be the identical, and these 2 are not mirror images. So these are 2 isomers of the what we call diastereomer. And of course, third variant is this one. This is a mirror image of this one, but they are identical. You can rotate this molecule and you can see you can get the same molecule. Also, if you have a previous one, tartaric acid, I have shown 2 chiral center. Now in this molecule hexose sugar, I have how many? 1, 2, 3, and 4 chiral centers. Okay. So D plus glucose, L minus glucose, a complete enantiomer, because all of them are different. This one was R, this is S. This one was R, this is S. This is S, and this is R. This is R, and this is S. So these are enantiomers. Between mannose and glucose, you can see that only one chiral center is different. Which one? The second one, because it is oxidized form. We normally the sugar we number it as 1. This is 2, this is 3, this is 4, and this is 5, and this is 6 carbon. So second carbon was in case of glucose as the R configuration. Here you have an S configuration. So these 2 are diastereomers. Sometimes we call them epimer. If you have a multiple chiral centers and diastereomers that differ in configuration at only one asymmetric center are called epimers sometimes. So all epimers are diastereomers, but all diastereomers are not necessarily epimers. So you just have to try to understand that if 2 diastereomers are differing by the stereochemistry of only one chiral center, as in case of mannose and glucose, so they will be diastereomers, of course, but they are also epimers. So keep this in mind. So how about the galactose? So if you compare galactose with a glucose, you can see the stereocenter. This R has become R. These are S here. So second, third, and fourth. So fourth carbon has a different stereochemistry. So these two, galactose and glucose, are also diastereomers, and of course they are also epimers. Similarly, you can say like a mannose and galactose. Mannose and galactose, where you have a R and S. This is S and S and R. So they are diastereomer but not epimer. So mannose and galactose are two diastereomers, but since they differ by more than one chiral center, asymmetric center, that is why they cannot be called epimer, and they are simple diastereomer. Is clear? Now enantiomers or diastereomers have properties. So physical properties of enantiomers. So two enantiomers, as I have shown before, D plus glucose and L minus glucose. And how will you know differentiate between the two? They have the same melting point, they have the same boiling point. Of course, sugar will not have a boiling point, but any other molecule, if the two enantiomers like a lactic acid and all, same boiling point, they have the same density, they have the same polarity, and many other physical properties, and they cannot be separated by column chromatography. Normal silica gel column that we use to separate molecules cannot be used for separating enantiomer. And identical spectral properties like NMR, IR, or any other spectral property that we'll learn a little bit about this methods, NMR for example. So they will be same. So only thing that differs between these two molecular enantiomers will be property that depend on the shape of the molecules, can be different. Optical rotations will be the same again in magnitude, but opposite sign. So if one isomer rotates the plane polarized light in one direction, the other enantiomer will rotate it in the opposite direction. Suppose one enantiomer has rotation like a plus 30 degree, the other one will be minus 30 degree. So they will be same magnitude, but completely opposite in direction. So we'll come to that, optical properties. Whereas diastereomers can have a different properties, physical properties also. Of course, they have the same molecular formula and the mass, but differ in all scalar properties like boiling points, melting point, density, refractive index, thermodynamical and spectroscopic properties, and even their reactivities, biological properties and optical properties, and so on. And of course, enantiomers will also have one different is like a biological property, because one enantiomer may bind to a receptor site, but the other enantiomer will not be able to. So molecular recognition is one also important aspect of the enantiomer. And same thing about the diastereomer. They have a different optical properties. So if you go back to D plus glucose and L minus glucose, they have the same molecular formula, they have the same mass, they will have the same like a what you call NMR, IR, and many other properties. But one thing that will be different, that one of them will rotate the plane polarized light in the positive direction in the right hand side, and other one on the left hand side. But these two molecules, mannose and glucose, are completely different. They can be separated by chromatography. They have a different molecular weight, same molecular weight, but spectral properties will be different, and so on. So keep this in mind, that enantiomers we can only distinguish by the specific rotation. And so we'll come to that one, specific rotation in the next class, that what is very important about chiral molecules. As you can remember, like a this properties like a specific rotation, a very old concept, and people were able to measure the specific rotation, and that's how like a Pasteur, he was able to separate those two chiral molecules of the tartrate salt, and so he could find out, one of them is a dextrorotatory and other is levorotatory, and they are two different enantiomers of the same molecule. So in the next class, I will be telling about the optical activity and what is very important property chiral molecules. And if you have any question, you can ask me now, or you can clarify with the teaching assistants on Friday classes.
Yeah, so sir, I had a question. So in the slide on which you had defined enantiomers and diastereomers, so can you go back to that slide once? Slide number 28.
Okay, is this the one which you are able to see?
No, just the one before. Just the one before.
Okay, fine. Yes.
Yeah.
Yeah.
So here you have defined diastereomers as those stereoisomers of a chiral molecule with two or more stereocenters having different configurations.
Yes.
But I mean,
at least one
diastereomers. Yeah.
Yeah.
So,
for example, this one in the middle, I can show that this is S and this is S, whereas S and R. So this becomes a diastereomer. Of course, in this case, it will be epimer also because there's only one chiral center is different. Tell me.
Yeah. So in the modern day terminology, will this be a diastereomer, or anything which is not an enantiomer is a diastereomer? Like modern day terminology also says cis and trans to be diastereomers.
Cis and trans, like olefins, cis and trans olefins.
Yeah.
We normally don't go because there's a different terminology there, E and Z configuration. We don't call them diastereomers because there's no chiral center there. But to give a configurational nomenclature, we use trans and cis, but we don't call them RS kind of thing. So normally I would assume that like a molecule will be called enantiomer or diastereomer if it has a chiral center as shown here, and they at least one of the centers have a different stereochemistry than it is diastereomer. And of course, in the same molecule, in the within the same molecular formula and same like a substrate. I will not call two different molecules diastereomer, but same molecule, this will be called diastereomer. Not olefins. Olefins, I don't call them diastereomer. I don't know if it is different. So normally I will say E and Z.
Yeah, so IUPAC has like the definition which they are suggesting is that anything which is not an enantiomer will be a diastereomer, starting from cis trans to any other systems, maybe maybe chiral, maybe achiral, whatever be they.
I'll check that part, but normally for olefin I don't call them diastereomer or because they have no chirality. So enantiomer and diastereomer will not get confused at this stage, and so it is related to also chiral property and many other properties. So I'll check that part if olefins are called diastereomers or not, enantiomers or diastereomers.
Okay, sir. Yeah, it's there in Nasipuri as well.
Okay.
Sir, so can you please re-explain slide 27?
Let's see this one.
Yes, I couldn't understand its transformation. Can you please re-explain it?
Yeah, I mean, like you see this one, oxygen 1 and this carbon here, right? Oxygen 1 and this carbon, this bond. Can you see the cursor here?
Yes, sir.
Yeah, this bond you rotate on the left hand side. Yeah, no, right hand side, sorry, right. Rotate towards the right.
Yes, sir.
Then you can see that hydrogen is coming slowly above the plane and carboxyl is going towards your right. If you rotate this bond slightly, don't only that bond you rotate, and then you can see when you rotate that carboxyl is going towards the right hand side, and hydrogen which was below the plane, now it is coming above you.
Yes, sir.
And then you can see that in that like a rotation, hydroxyl that on the top is going below the plane, and this methyl also going below the plane. So little exercise if you do, and then of course once you draw like this, then this is the Fischer projection, And then, you know, I have drawn hydrogen horizontal line here, carboxyl group on the right hand side, hydroxyl on the top, and methyl. So when you draw like this, then if it is clockwise, this is S, right? And if this carboxyl was here, then you go like anti-clockwise, then it will be R.
Yes, sir.
Okay. So little tricky, but you play around with the molecule, rotate and try to visualize what it will look like. And then from there you can also determine the stereochemistry. For example, here. So now I'm not rotating or doing anything. I have gone, you know, from oxygen is highest priority. This is the second. And this whole portion is the third priority. So 1, 2, and 3. So now this is, forget about the hydrogen. So you are going in anti-clockwise fashion. So this is R.
Yes.
Stereochemistry and in the Fischer projection. And same thing on the bottom one. So this hydroxyl is first, and this is the second, and the whole thing here is the third priority. So 1, 2, and 3. So this is also anti-clockwise. So this is R. But if you draw any structure like as I've shown here on the left hand side, then you have to go, you know, hydrogen is away from you, and then you go from 1, 2 to 3. If it is like anti-clockwise, then this is S. But in the Fischer projection, you follow different way, you know, opposite to that one. So then you will get the stereochemistry. Little bit you practice and take any molecule, draw the structure. You can have a, you know, like a tartaric acid which has 2 carbon. You can have a 3 carbon or 4 carbon, different other sugars, and try to determine the stereochemistry. So we'll also, you know, do a little bit more exercise. I think in the TA, in the classes, they will show you how to know R and S stereochemistry. And priority rules also very simple. So you go through them once again, and we'll also talk about a little bit confusion will come here, but with little practice you can see that why acetylene has a higher priority than tertiary butyl, or simple, you know, ethylene has a more priority than isopropyl, and similarly carboxylic group has a higher priority than COH3, and so on. Other things are I don't think very difficult for you to understand. All right. So in the next class, we'll talk about the optical activity, one of the most important property of the chiral compounds, and we'll go from there.
Sir?
Okay. Yeah, anybody else have any question?
I got briefly disconnected when you were explaining about phantom atom. Can you explain it a little bit?
I also don't follow, but anyway, so basically, don't worry about what the nomenclature, phantom, and all those things. But what you do is this carbon, the green color, is attached to this oxygen. There are 2 bonds, a double bond is there in between. So when you write inside the bracket, so you put, because this same carbon is attached to 2, as if it is attached to 2 oxygen. So oxygen 1, oxygen 2, and then of course the hydrogen is there, aldehyde. In this case, you don't have the multiple bond. Same thing here, you know, basically what we have done, I have not drawn like a bracket kind of thing, but you can see that this carbon is attached to 1 hydroxyl and this oxygen, and 1 more oxygen I have put just to show that this is kind of like we have assumed that this is another oxygen atom it is attached to, we have put in a bracket. So, and double bonded oxygen also, oxygen I put here, and this carbon I am putting here. And because this is attached to 1 carbon, that is obvious to you, but this is also double bonded carbon. So I have put 1 more carbon that I have put one within the bracket. And so since one of the oxygen is attached to 1 carbon, so I have given this one a higher priority. So bottom one also same thing, you know, like this carbon is attached to this carbon on the left, and also since it's a double bond, I put 1 more carbon, and of course it has a hydrogen and hydrogen, 2 hydrogens are there. And inside carbon also has one carbon attached here, one hydrogen, and one I have put here.
Okay,
So it
sir,
is
got it.
considered to be replicated at both ends of the multiple bonds. So whether you have multiple bonds between one carbon and one carbon on one carbon on oxygen, so it is replicated on both sides.
Okay, yeah.
Hello, sir.
Mm.
Yes, so for the example that you have given for the olefin moiety, you have compared it with the isopropyl, right? So instead of isopropyl, if there was sec-butyl, then what would the comparison be?
Sec-butyl, if you go, it will have, I think, one CH2 in between, right?
Yes, so for
So
one,
that is the different, you know, then in the first carbon itself, you are able to decide that, you know, you don't have to go to the other substituent there. So
why?
slightly similar is here. For example, in this substrate at the bottom, you can see that you have a CH2. So obviously, you know, like this carbon here, which is nitrogen and nitrogen, two nitrogen, but here you have a two hydrogen. So this
No, in
obviously gets a
sec-butyl also you have two carbons only.
Huh?
On one side it is C2H5, on one side it is CH3 for
CH2.
sec-butyl.
So if it is a sec-butyl, you have a CH2, then CH, CH3, CH3, right?
You have you have
Or
CH.
you know, like it will have a methyl and methyl here, right? Or maybe that one. That
Yes,
one you mean.
so,
Yeah,
no,
one
over
methyl
here
and
it
one
is
methyl here.
CH3, right?
Ah.
So I mean over in sec-butyl there will be CH, and on one side it will be CH2 CH3, and on the other side it will be CH3.
Yeah. So if that is so, also you can also do that exercise. This carbon, for example, attached to one carbon, another carbon, and one of the substituents here is like a carbon, and this is a hydrogen. So if I have then in one carbon here, two carbon here, but then there is a hydrogen there, and this is multiple, so this gets a priority, this one. So as a sec-butyl also will have a less priority than this multiple bond one. So olefin will have a more priority than the sec-butyl also.
Okay, sir. Thank you.
Anybody else have any question? Okay, if no, then all these things are there in the slide, and I have also uploaded the new schedule, corrected schedule, so you can see those, you know, classes and the exams are there. So we'll again take it up from on Thursday. All right. I'll unshare. I'll leave.